All right, make sure I'm recording. Good. That worked the first time. Amazing. All right, so what we're going to look at in this section is basically how to form new functions from existing ones, right? And the easiest, most natural way, I would say, to do that is the arithmetic combinations, right? You have two quadratic functions, 5x squared and 3x minus 2x squared. You can form a new one by adding those guys together, subtracting them, multiplying them, and even possibly dividing them, right? So remember, a function for us will just be an expression that passes, whose graph passes the vertical line test. And so ultimately, all we have to do is just make sure that we know what the domain is for these algebraic expressions, and the rest of it is, since we're not doing anything to the output, it'll automatically pass that vertical line test. And so what I want to do is talk about these four natural arithmetic operations just in general first, and then we'll look at some examples of how you compute with them. So it's actually a pretty easy section. The only thing that basically is the wrinkle is that it involves more algebra, right? So back to that chapter that we talked about with how to deal with polynomials, how to deal with rational expressions and that sort of thing. That will come into play, right? But you're practiced on that, so hopefully that won't be too much of an issue. All right, so suppose f and g are functions. The new you can form a new function called f plus g just by adding those two guys together, f of x and g of x. And in order for the sum to exist at a value, right? So in order for this function to be defined, what has to happen is, well, f of x had better be defined at x, and the other function g had better be defined at x. If one of those isn't defined, the sum can't be defined, right? You can't add two things together that don't make sense, right? So that's all you have to do. And the sum is just equal to that. You literally just add the functions together. For the difference, same idea. As long as both f and g are defined at x, the difference function is the difference of those functional values. You just subtract them. Product is the same way. Quotient is the same way, right? Only here you have to make sure that not only are f and g defined at x, g of x cannot be 0, right? If g is 0, then you're dividing by 0, and you can't do that. All right, and then up here, notice with the products, I had mentioned a special case. If one of the functions itself is a constant, then oftentimes what you'll see is the function a number times f, like 2f or minus 3g. You'll often see the notation written like that. And all it means is multiply every one of the functional values f of x by that constant. All right, so let's look at these examples. So I just give you these three functions, right? We know all about lines and we already know about quadratics. So you're familiar with these functions. The domains of these three functions are all real numbers. And so we're not going to have any domain issues for the sum, difference, and product. What we will have domain issues for is the quotient. So we have to be a little bit careful there. All right, so let's look at f plus g, right? F plus g of x is defined to be f of x plus g of x, right? And so I'm going to add 2x minus 1 and 5x squared. But notice all we're doing here is adding polynomials together, which you know how to do, right? You just add like terms and then simplify. So the only thing that happens here is that the ones cancel. And so what we get is 5x squared plus 2x. The domain is all reals because the domains of f and g were both all reals. So the function's defined everywhere. For g minus h, I'm going to take g of x minus h of x. So just remember the order makes a difference here, right? If you subtract in different orders, you're going to get different values. So just be careful there. G of x is 5x squared plus 1, and then h of x is x squared minus 9. If I'm subtracting these, I'm distributing that negative sign through, right? And then now you just add like you normally would polynomials. Add together like terms to get 4x squared and then plus 10. All right. Again, the domain's all reals because g and h have a domain of all reals. All right, the product, same way. F of x and g of x are these two functions, and I have their product, right? But now we're just having to simplify that. All you have to do is FOIL that out. Remember that first, outer, inner, last, which is really just the distribution property applied several times. So if I do that, I do get 10x cubed from the first terms. Middle terms, I get minus 5x squared plus 2x and then minus 1. Where we have to be careful here now is f over h, right? So just symbolically, f over h is this function. That's a rational function. And so technically here, what you'd want to do is ensure that there are no common factors in the top and bottom. But you can kind of look ahead and say, well, x squared minus 9 is a difference of squares. That just gives you x minus 3 times x plus 3. And neither of those factors can be canceled with 2x minus 1. All right, and so this cannot be simplified algebraically. But what you have to make sure of now is to determine the domain correctly. Right? Even though both f and h have a domain of all reals, as an entity, this whole quotient does not have a domain of all reals because it has a denominator, right? And so you have to throw out any x value that makes the denominator equal to 0. Those values would be plus or minus 3, right? And so the domain of this quotient is technically this set here, all real numbers except for minus 3 and positive 3. All right, your turn 1. So go ahead and give this a shot. I won't, I'll show you the answers here in a minute. Just try, it's basically the same idea. You have 2 quadratics this time, and then you're just performing these 4 arithmetic operations. So see what you got. Just be careful again with domains. All right, so if you add, subtract, and multiply the natural way, you get these functions. Right? And the domain of all of those 3 functions up here, those are all minus infinity to infinity, right? Because quadratics have a domain of all reals, and so the sum, difference, and product would have a domain of all reals. The quotient is here. It does not simplify, right? You should check to see that if you factor the top and bottom, you don't get any common factors, but you don't. But now in terms of the domain, you have to exclude any point that makes the bottom 0, and that would be minus 2 and 2. All right. This one, same idea, but now it's worse because the functions you're dealing with aren't polynomials themselves, they're rational functions. And so you have to remember how to add, subtract, multiply, and divide rational expressions, which we did back in that very first chapter. Right, so this will take you a little longer, but it's not because the concept is more difficult, it's because the algebra is slightly more involved, right? So take the time, do that, and we'll talk about that once you get back to the video. All right, so let's look at the sum. If I add those 2 guys together, remember what you have to first do is get an LCD. But to get an LCD here, you just use both denominators. And so I need to multiply the top and bottom of the first guy by 3x plus 2, top and bottom of the second guy by x minus 4. And then if I do that, both resulting fractions end up having this LCD, right? And so the fraction that I get, the big rational expression I get after having done that, is this thing. Notice now I'm not multiplying out the denominator ever. You never multiply out the denominator of a rational expression. There's no reason to. Because ultimately what you like to do is cancel like factors in top and bottom, and so you just have to refactor it anyway, right? It does you no good to multiply out the denominator. However, you do want to multiply out the numerator in an attempt to then factor the simplified result. And so what I'm doing here is foiling out these first terms, and then I'm squaring that guy again by foiling, adding like terms to get this, and it turns out that that does not factor. Right, so it's not going to cancel with any, it's not going to end up canceling anything with the bottom. All right, if you subtract, same story, same LCD, right, but now when I simplify, I get a different expression in the top. Again, that one does not factor, but had it factored in and it had a same factor in top and bottom, you would cancel that factor, and that would then lead to a simpler result. All right. Notice that in both the sum and the difference cases, right? In both of those cases, you end up with the domain equal to everything but 4 and minus 2/3, right? That's the only time that that function becomes undefined. The product is nice, right? If you multiply these two functions, note that what you don't want to do here is multiply across the top and the bottom separately. Again, you're trying to simplify these things, not make them gargantuan. And so what I'm going to do instead, remember, to multiply fractions, you can cancel factors in top and bottom that are the same. And so I'm going to cancel out the x minus 4s. That gives me this guy. Okay? But here, don't forget, you cannot cancel this further. You cannot simplify it. You can't cancel those 2s or those 3s because those are terms being added, not being multiplied, right? They're not factors. You can only cancel factors. All right. And then finally here, Benjamin. Finally here, if I divide f by g, right, that's really a complex fraction. It means to multiply the top by the reciprocal of the bottom. That's what I do. So I'm flipping over the bottom and multiplying. But now I can't cancel anything out. There's no x minus 4 in top and bottom. And so the end result is just this quadratic over x minus 4 squared. Oh, my dog is whining. Okay. Good. So if you, all right, so suppose you wanted to compute any of these three functions or any of these four combinations at particular values of x, but you didn't have an expression, you had a graph, right? So for example, suppose I gave you that these were the graphs of my functions f of x and g of x, and I asked you to compute these quantities, right? You don't have to have an expression into which to plug your x values. You can just use what the y values are on each of these graphs at that x value to determine the functional values each time. So for instance, let's look at this. So f plus g of minus 2, by definition, that's f of minus 2 plus g of minus 2, right? That's just how it's defined. But f of minus 2 is the y value at minus 2. Well, that y value is 1, so that's equal to 1. And g of minus 2 is the y value on the graph at minus 2. That's 0. And so I'm plugging in a 0 there. 1 plus 0 is 1. And so f plus g at minus 2 is equal to 1. Okay. Similarly here, g minus f of 0 is g of 0 minus f of 0. G of 0 is the y value on the graph of g when x is 0. That's 1. F of 0, notice that f of 0 has an open hole only. There's never a closed point. And so f of 0 is not defined, right? 0 is not in the domain. And so that means this part of the function isn't defined. And so the difference cannot be defined there, right? So g minus f of 0 is not defined. If I want to multiply f times g of 4, I want f of 4 times g of 4, right? But f of 4 is the y value on the graph at 4, that's 1. G of 4 is the y value on the graph at 4, which is 3. And so I get 1 times 3, which turns out to be 3. Right? And then finally, the quotient f over g at minus 2 is f of minus 2 over g of minus 2. F of minus 2 is 1, just by looking at the y-coordinate of the graph. G of minus 2 is 0. And so what you would get, unfortunately, here is 1 over 0. 1 over 0 is not defined, and so f over g of minus 2 is not defined. Okay. However, if you looked at the reciprocal function instead, if you looked at g over f at minus 2, then I'm flipping those over. In that case, I'd have 0 over 1. That is defined. That would be 0. Right? So just be careful with quotients and differences in terms of what the order of the functions are, where they are in the top or the bottom, because that will make a difference in general in terms of the value or possibly the domain. All right, so the next one is your turn on this. I give you these graphs, and I want you to compute several values. Right, so go ahead and try those and see what you get, and then check yourself afterwards, and I'll talk about a couple of the more different ones. All right, so for 5, remember, we hadn't looked at constant multiples yet, but I did mention back before when we talked about products that a special case of a product of two functions is one where one of the functions is always a constant. And so I write this as that constant times the function. So what this notation means is to compute f of minus x and then multiply that result by minus 3. Okay. So to get f of minus 6 again, go to the graph of f. Here's x equals -6. Go up to the point on the graph. Well, that y value is 1. And so f of minus 6 is 1. So this function at minus 6 is minus 3 times 1, which is minus 3. All right. Same way here. This looks worse, but it really isn't that bad. You have a sum of two functions, right? So I know that I'd have this function at 3 and that function at 3. But remember what 2g at 3 means. It means to compute g of 3 and multiply by 2. And this guy means take f of 3 and multiply by 5. G of 3 is just the y value of the point on the graph at 3. That's 1. Right? And then f of 3 is here. F of 3 is the value of the point on the graph, and that means the closed point. And so f of 3 is not 2, it's not 8, it's actually equal to 3. That's where the closed point or closed circle is. That would be where the functional value is obtained from. So f of 3 is itself that y value, which is 3. Okay. All the other ones are similar to what we had done, so make sure you check yourself on those. Okay, so what if I gave you, again, some functions and I asked you to compute a more elaborate arithmetic combination, right? So you don't have to just add, subtract, multiply, or divide just two functions. You can have these combinations of several functions. But the way you compute them is exactly the same way, right? So for instance, what this function means is to take f of x minus g of x plus h of x. Right? It's exactly like you would have had just for two functions. It's just now we're applying it to 3. If you plug those in and just simplify like you normally would polynomials, that's what you end up getting. Okay, so it's no different than before. The only caveat here is the domain now. If you're using 3 functions to form a new one, then the domain of this new function has to be the intersection of the domains of all the pieces. So in other words, every one of the functions you use to define that function have to be defined at that x. If they're not, then the whole thing breaks down, right? You can't add 2 plus 3 plus undefined, right? That doesn't make sense. And so the x values you clunk in have to belong to all of their domains. All right, and then I'm going to have you read this example again. It's just another one of the word problems. Take a look at it, just see kind of what's all involved in modeling, and then try that your turn. The answer's in the back of your, the end of the section in your PDF, and see what you get. All right, try the homework problems. Most of them are fairly straightforward. Some now involve radicals, so just be a little bit careful how you simplify them. But by and large, these should not be too bad initially until you get to about I would say number 9 is not hard, but it's a little bit more involved. 9 and 10 will cause a little bit of heartburn, maybe number 7. Okay, let me know how it goes.